Okay, back to honors pre-calculus. Now we're going to be talking about parametric equations. Parametric equations are basically another way to write functions or equations. Usually we write it in rectangular form or Cartesian form, where you get y is equal to some function of x, let's say 2x. Now in parametric form, we have two functions, x of t and y of t. They both are based on some external variable. In this case, we're using t. It could be anything, but most of the time it'll be t. So what it'll be is basically it's equal to some value, and then y is equal to some other value. So for simplicity's sake, let's say x of t is equal to t, y of t is equal to 2t. This looks complicated, but it's actually the same exact as this rectangular equation over here. And we'll get into converting between them a bit later. But few things first. This is a set of parametric equations. T is called the parameter because it's the variable that both equations are based on. It's the independent variable of both functions. Okay, let's now talk about converting between parametric and rectangular. So for converting from rectangular to parametric, it's always going to be pretty much simple. You just say x equals t and y is equal to basically the same exact function, but with t replacing x. So most likely you're not going to be asked to convert a rectangular into parametric, but let's talk about converting parametric into rectangular because that's a bit trickier. In this case, it's really easy because x is equal to t. So if you have a t, you can just replace it with an x because you know x equals t, and you get y is equal to 2x. Simple. But if it's a bit harder, like let's say it's equal to t squared and 5t, then you would have to isolate for t. So say t, you take the square root of both sides, you get t is equal to root x. Technically, it should be plus or minus root x because this would actually form a horizontal parabola. We talked about that in our conic sections video, actually. So technically, it'll be plus or minus x. Plugging that into here, we get y is equal to plus or minus 5 root x. That wouldn't be a function per se, but you can still represent it using parametric equations. However, in most cases, you won't use parametric equations to represent something like this because parametric equations usually describe motion. Now, the reason why it won't work, the reason why all motion equations have to be functions, if you have something like this for position, that means at a given time, let's say this right here, you have two positions. You physically cannot do that unless you can clone yourself and go somewhere, which according to physics right now, you cannot do. So let's just say that this has to be a function. There are some cases like quantum mechanics where you can have multiple of objects, quantum objects that travel, but you're most likely not going to encounter that in honors pre-calculus. I really hope you don't encounter that in honors pre-calculus. Okay, so we just talked about some of its applications, motion especially. The reason why is because we have that third variable, the parameter t, and t usually stands for time, as you might imagine. So projectile motion is a very important application of parametric equations because you would have time as well as the horizontal distance as well as the vertical distance accounted for. And to make sure why this is important, let's say we have the generic example is a fox and a rabbit. We have a fox chasing a rabbit. So let's say the rabbit is defined by this function, the fox is defined by this function. It's both the position. Let's say this is an xy plane. You're staring at it overhead. It's not vertical position because foxes can't fly up like that. But let's just say you're staring from above, x and y. In this case, it's not horizontal and vertical. It's just a coordinate plane on the ground. This is the definition of its paths. You would say, obviously, the fox catches the rabbit because this is R, this is F, they intersect. But if we were to use parametric equations, and we might find something different. Might, actually, not you will, but you might. Let's say at t is equal to 0, the fox is here, the rabbit is here. At t is equal to 1, the fox is here, the rabbit is here. 2, here, here. 3, the fox is here. The rabbit reaches this intersection point. 4, the fox is here. The rabbit moves out here. 5, the fox finally reaches this intersection point, but by that time the rabbit is already here, and then they continue in their journeys. And they don't actually meet each other. That's very important, because it's like if someone was in the specific spot 5 seconds ago and you come to that spot, but they're not there. You don't really catch them, do you? You're in that same specific spot that they once were, but not that they're right now. If you were to just look at those two lines on an XY plane, you would see that, yes, they do intersect. The fox catches the rabbit. But if you were to look at them using parametric equations, you would see that they intersect at different times. So time does really matter in physics especially, which is why parametric equations are really useful. Now, that leads us right into how to graph parametric equations, because we just tried graphing it just by plotting points. It didn't really work out well. Well, that's basically how you're supposed to plot it, graph it anyway. You create a table. In algebra, when you first learn how to graph functions, you would create an xy table, have random values of x. 0, you would get a y value of 0, 1, you would get 2, and so on. In this case, we have something similar. We have a t, an x, and a y. Let's say, for example, x, I'm just going to write x equals. You could write x of t equals or just x equals. Usually you write x of t because they're parametric functions, but you can also write x equals in some cases. Let's say you write x is equal to phi t and y is equal to 2t squared. So when t is equal to 0, what's x? Well, you just plug it in, you get 0. Y is also 0. When t is equal to 1, you get 5, and you plug it in, you get 2. 2, you get 10, and you plug it in, you get 8. 3, you get 15, 18, and it goes on like that. Then you graph a function, but you only care about its x and y values. You do not plot t anywhere, but you can, if you want to, and usually it's recommended, you just write t equals 0 at every point you graph. So you plot 0, 0, then you plot 5, 2, you write t equals 1. And this is just for like the fox rabbit example, just so you know at what moment something happens. You have 10, 8, t equals 2, and then the next point is probably going to be off the grid, but we can connect the graph anyway. And graphing it can actually be a tool for finding out what equation it is. This is a parabola. Again, if you want, watch our conic sections video to sort of find out how to graph parabolas in a pre-calculus way instead of a algebra 2 way. Okay, that's graphing parabolas. Graphing parametric equations. And we just have one more topic in this. It's going to be a rather short video. We just have one more topic, and that's projectile motion. We said that's an application of parametric equations, but how can we do that? Well, x would be the horizontal distance, y would be the vertical distance, and t would obviously be time. You're going to get a set of equations. X of t is equal to the horizontal function, y of t is equal to the vertical function. And there is a formula to calculate it. Let's assume you start with an initial velocity v0. You start at a point h comma k. And let's say it's at an angle theta. So assuming it's like this is the angle theta. You start at h comma k. And you start with the velocity of v0. Now this isn't a vertical or horizontal velocity, it's a total combined vector sum velocity. Again, if you want to refresh on vectors, we have a vector video as well. To find the vector sum, as a little refresher, is just using Pythagorean theorem of the horizontal and vertical components. That's the magnitude. So we would be doing something here. How to separate it though is where we get trigonometry, and that's where the theta comes in. If you have some magnitude r, then the horizontal would be r cosine theta, because if you consider this as theta, you just get a right triangle. Moving this vertical over here, you get r sine theta because it's a right triangle. And that's basically how you calculate each component of a vector. Let's do that here. We know that from physics, we know that the equations for motion are the displacement, the horizontal displacement would be the starting velocity in the horizontal direction times the time, or the change in time actually, and the change in vertical height, or vertical displacement basically, is technically equal to negative 16 times delta t squared. Now the reason it's negative 16 is because we're going to be talking about feet per second, and in this case it'll be feet per second squared because it's acceleration. But in usually in physics we would use meters per second and meters per second squared. Therefore it'll be a different value. This is actually half the value of gravity in feet per second squared. Then you add the y velocity or vertical velocity times delta t, and if I can and that's basically it. However, we have one more thing to do, and that's add h and k, because you might start with a position, and we said that we will start with the position in this case, so I sort of crammed it, but you basically add x0 to the x equation and y0 to the y equation, and because of that we can get rid of this delta in front and just say that the final x, because otherwise it'll just be the displacement. It doesn't matter where you start, the displacement will be the same, but in this case it'll just be the final x and the final y value. Alright, how do we convert that into this parametric equation? And what's Vx? Well, that's going to be the magnitude of the velocity times cosine theta, because that's the horizontal. So we get V0, that's the starting velocity, cosine theta, times t. It's a function of t, so we need t. And then we have to add x0 to it. Most likely you're not going to get an x0 value, you're going to get a y0 value though. X0, or in this case, since we said specifically it's h, we're going to change that to an h. As you might imagine, it's negative 16t squared plus y0, which would be v0 sine theta. That would be the y component of the initial velocity, times t plus k. Y0, or basically k. And that's basically the parametric equations for projectile motion. You can plug that in when you're given v0, hk, and theta. Most likely you're not going to be asked to simplify v0 cosine theta, because then you're going to lose precision in your answer. You're going to get some decimal most likely, unless it's like 30 degrees or 60 degrees, 45 degrees, something that you know is you memorized in trig. So more often than not, you're going to leave it as some number times cosine of some number and some number times sine of some number, instead of simplifying it down using your calculator. So we talked about parametric equations, how to convert them, how to graph them, and now we're talking about an application of them. That's basically it for parametric equation. That's basically all you need to know for honors pre-calculus. There are other applications and other things we can do with them, but that's not needed in honors pre-calculus. So without further ado, that's it for this video. See you next time.